Welcome back. Today we're going to build on some ideas from Calc 1 and define this idea of Taylor polynomials, which is improved approximations to the functions that we are kind of looking at. So I've got a function I've drawn here, and I've sort of sketched out the idea of the linearization we saw in Calc 1. And the linearization of a function is just the straight line approximation to that function at a point. So the value of that function at the point is f of a, and then it's going to have a straight line approximation with slope given by the slope of the curve here. So the curve, the yellow curve, has slope f prime, right? The derivative is the slope. And so this is the equation of a line with the slope f prime that passes through the point a, f of a. We called it a linearization in Calc 1. Well, our job now is to go to the next level. What we're going to do is, instead of thinking about just the straight line that approximates this yellow curve near the point a, f of a, imagine I could also fit a parabola that was really close to that curve. So that parabola might be a better approximation than the straight line, right? Certainly when I get away from the curve, the parabola is not going to approximate it, but close enough to that point, a parabola might be a better approximation. Or a cubic might be a better approximation, or a fourth degree polynomial. So we can approximate the function f near the point we're looking at with different degree polynomials. And these things are literally called Taylor polynomials. And that's what we're going to talk about today. And we've already seen the first degree Taylor polynomial because it's precisely what we called the linearization of the function at the point x equals a in Calc 1. So we're just expanding that idea of approximation to higher degree polynomials. So our linearization was selected precisely because the value of the linearization at the point a is f of a. Think about plugging that in here. This is just f of a. In other words, it passes through this y value. And the derivative of L at the point a is equal to f prime. So think about differentiating this. You get a constant, and that constant is that slope. So I chose this function L, so it was a linear function that obeyed those two properties. So what I'm going to do is generalize that idea. So I want a function f of x to be approximated in general by an nth degree polynomial. And here's a general nth degree polynomial, and we've chosen it to be sort of centered at x equals a. Just like before, this one was designed so that when I plug in x equals a, this term disappears and I'm left with this constant. And so looking at that, if I plugged in x equals a to this part, I'm going to be left with a sub naught. So what I want is f of a to equal g of a, right? I want those to agree. And also, I want f prime of a to be the same as the derivative of g, because when I was using this linear approximation, I had the value of the function. This was L, but now I'm calling it g. So the value of g and f agree, the first derivative of g and f agree, and in fact I want this to be true all the way up to the nth derivative, because when I was using the first order approximation, I wanted the first derivative to be equal to the first derivative of the function. So now I want the nth derivative of the function for this nth degree approximation to be the nth derivative of g at the point a. And so we can start calculating those things, right? We can write those down. And we don't know these coefficients a0, a1, a2, but we know they're constants. And so we can start taking derivatives, right? The first derivative is going to differentiate this term and leave with just a1. Derivative of this term is going to be 2 lots of a2. There's going to be 3 lots of a3, x minus a squared, and so on. In fact, that should be an n minus 1. And then the next derivative is going to be, well, I've got a 1 there, so it's going to, this is a constant, so the derivative is 0. So this is 1 times 2 a2 x minus a is now gone. That's a 0th power, so I don't want that at all. And the next one is, well, there's a 1 there and a 2 and a 3. a3 x minus a to the power of 1. That's from this term. And then the next one is going to be something similar, which I didn't write down before, but then it's going to go up to the n a sub n, well, n minus 1 a sub n x minus a to the n minus 2, and so on. Right, the third derivative is going to be, well, this is now a constant, so the third derivative is going to be, leave me 1 times 2 times 3, a3, and the next term is actually going to be, well, we would have had a 4 there, and then a 3, and then a 2, and you pick up this term, and so forth. So the next one, the fourth derivative, just to write down the last one, the fourth derivative is going to be, well, this is now a constant, so it's just going to be 1 times 2 times 3 times 4, a4, plus some other terms, and then the last term is going to be some numbers, but then there's going to be an x minus a to the power of, well, that's n minus 4. What I want you to notice is our conditions here are all about the value of the two functions at x equals a. And when I plug x equals a in, every term is 0 except for the very first term. When I plug in x equals a, all of those terms are 0. In this case, from there off to the right are all 0. So when I plug x equals a in here, I'm left with that single number, or that single number, or that single number, or that single number. Writing them out, and we see the pattern holds here too, g of a is just a sub 0. So g of a is a sub 0, but that's got to be equal to f of a by design. Right? And we know g prime of a is equal to a1, and that's f prime of a. And then g double prime of a is equal to, let's have a look, it's 2a2. I'm going to write it as 1 times 2 times a2, and that's got to be f double prime of a. And then the third derivative here, it's going to be, well, 1 times 2 times 3 times a3. So 1 times 2 times 3, a sub 3. And that's got to be the third derivative of the function f. And then, I think you get the idea. The fourth derivative was 1 times 2 times 3 times 4, a sub 4. And that's f, the fourth derivative of a. Right? And so what we want to do is find out what these constants, what the a1, what the a2, what the a3, what the a4 are. And these green underlined things are going to tell us. Because you can see what a0 is. A sub 0 is f of a. A sub 1 is f prime. A sub 2 is f double prime divided by, well, that's 2 factorial, right? This value is 2 factorial. That value is 3. That's 4 factorial. It looks like in general that 1 times 2 times 3 all the way up to n times a sub n is going to be the nth derivative of f at a. And that's going to be true for all n greater than or equal to 0, right? And I'm going to think about here, I'm including 0. I'm thinking about the 0th derivative is just the value of the function itself. So that tells me what the nth term in this series is, or that tells me what any term in the series is. And I'm just changing this to a k because I'm using n to be the degree of the polynomial here, right? We've got an nth degree polynomial. It's not changing. We've got a fixed nth degree polynomial, but I want to know what all the coefficients are. I want to know what a sub 0 and a sub 1 and a sub 2 and a sub 3. I want to know all those values. So in fact, this formula tells me that it's the kth constant is going to be the value of the kth derivative of the original function f divided by k factorial. And that's going to be true for all k greater than or equal to 0 and less than or equal to n, right? So starting from the beginning and going to the end of the polynomial. That gives us all of the coefficients because k factorial, remember, is just this product, k factorial. And so this gives us the coefficients in what we call the Taylor polynomial. So this lets us put together this Taylor polynomial. We're literally defining the Taylor polynomial from this calculation. We started with a function g, and all I'm doing is plugging in our values for a0 and a1 and a2, and here are our values for a0 and a1 and a2, right? So in this case, this one tells us that a3 is the third derivative evaluated a divided by 3 factorial. And so plugging those in, our Taylor polynomial defined or centered at x equals a is going to be a0, which is just the value of the function, plus the first derivative of the function at a divided by 1 factorial multiplied by x minus a. And then the next one, right, I'm just using these values. There, that is a sub 1. And this value here is a sub 1. And then a sub 2 will be the second derivative with respect to a at, well, times 2 divided by 2 factorial multiplied by x minus a all squared. And then we'll have the third derivative at a divided by 3 factorial multiplied by x minus a cubed. And that will go up to our very last term. It's an nth degree polynomial, so our very last term is the function evaluated, the function's nth derivative evaluated at a times n factorial minus x minus a to the power of n. And this is called the Taylor polynomial. We could use this general formula up here to write it more like we've talked recently. So k is equal to 0 to n. This is not an infinite series, right? This is a finite series. We're starting from 0 and we're going to n, and this is the kth derivative divided, at a, divided by k factorial, this term, multiplied by x minus a to the power of k. And we're thinking here that when k is equal to 0, we're using the notation that the kth derivative when k is 0 is just actually the value of the function. So this is what we call a Taylor polynomial. And you can find this precisely in the textbook. It's the Taylor polynomial of degree n centered at x equals a. Let's have a look at what this looks like for a function f. Given a function f, let's find some Taylor polynomials and see what's going on. So for our first example, we're going to build the Taylor polynomials for sine of x, centered at a equals 0. And so what we need, looking at this formula for the nth degree Taylor polynomial, we want to build this for n is equal to 0, 1, 2, 3, and 4. Looking at this formula, you see that what we need are the derivatives. Up to the, well, if we're doing up to n equals 4, up to the fourth derivative of the original function. And so calculating those, f of 0 is the first thing we need. So f of 0 is just sine of 0, and that's 0. Right? But we also need to calculate some other things. We need f prime, we need f double prime, we need f triple prime, and we need the fourth derivative, which we can write as f4. And so calculating these is not hard, especially for sine. Derivative of sine is cosine of x. The next derivative is minus sine of x. The next derivative is minus cosine of x. The derivative after that is positive sine of x again. And so that means we can calculate all of these derivatives at 0. And you know that the sine of 0 is 0 and the cosine of 0 is 1. So these aren't too bad to write out. This is cosine of 0 minus sine of 0 minus cosine of 0 and back to sine of 0. Notice they're going to loop. After that, the next derivative would have to be cosine of 0 again, and so it repeats the pattern. Cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, but there's a negative there, and now we're back to 0. And so we can start writing out the Taylor polynomials. Right? Because the first degree Taylor polynomial is going to be f of 0 plus f prime of 0, x minus 0 to the power of 1, which is f of 0 is 0 plus f prime of 0 is 1, x minus 0. So this is just x. There's our first polynomial. So we've got the first Taylor polynomial, and let's draw a graph. And so here we see the sine function plotted between minus pi and pi. There's minus pi. And also plotted is the Taylor polynomial of first order, which is just the function x. And so we plot that. We can see it passes through the same point at the origin as the sine function does, right? It passes through 0. And it has the same slope at the origin. This is the linearization. This was in Calc 1 what we would have called the linearization. So that's kind of what we expect, right? So let's build T sub 2, the second order Taylor polynomial. And just writing this out, we've got the values up here. F of 0 is 0, and then we're going to add f prime over 1 factorial, which is 1 over 1 factorial x minus 0 to the power of 1. We already did that. But we're going to the second order, so the second derivative is 0 over 2 factorial, right? I'm just plugging in here. 0 over 2 factorial x minus 0 squared. There's our second degree polynomial. And notice that the second degree polynomial doesn't have a second degree term. It's still linear. It's still actually equal to what we have here. This is the same polynomial in this case. It's still x. But what about the third degree polynomial? Let's add that one in. Well, same idea, f of 0 is 0 plus the derivative of f prime at 0, 1 over 1 factorial x minus 0 to the power of 1. And then, the second derivative, which is 0 over 2 factorial x minus 0 squared. And then the third derivative, which is now minus 1 over 3 factorial x minus 0 cubed. There's the third degree polynomial. So when we write this down, we've got x minus 1 over 3 factorial times x cubed. And 3 factorial is 6, so this is x minus 1/6 x cubed. And so there's our degree 3 Taylor polynomial. This is the third Taylor polynomial that approximates the sine function centered at the origin. So what you see here is the sine function in blue plotted on the graph with the first and the third Taylor polynomials, right? So the first Taylor polynomial was just a straight line through the origin. The third Taylor polynomial still goes through the origin, but it's now a cubic, and so you see it has a minimum and maximum here, and they're getting close to the minimum and maximum of the actual sine graph. It at least approximates the idea of the sine function in terms of there is a minimum and maximum around there, although clearly it gets away from the behavior of sine as you move away from the origin. And in fact, we know for this green function, this cubic, it must continue down to the right and up to the left for all t, because this function is a negative x cubed kind of shape. And so it has to go off to positive infinity when x goes to negative infinity, and to the right it has to go down to negative infinity. So it can't capture the whole oscillating idea of a sine function, but it's getting better. Let's have a look at higher degree Taylor polynomials. All right, so this is a little animation, and it shows us the sine function there in kind of that burnt orange color, whatever that is. And you can see the first degree Taylor polynomial is there. That first Taylor polynomial, that's just the line y equals x. We can see the slope is 1 at the origin, like it is for sine. And then the third degree Taylor polynomial looks like this. And then we add the fifth degree polynomial, and it looks like that. And then the seventh degree polynomial looks like that. These are all odd functions, which is why we've got fifth and seventh degree. There's no fourth degree. The fourth degree polynomial, the fourth degree term is 0. The fourth degree term is 0 precisely because of all of those derivatives we calculated, right? The fourth degree term is 0. This pattern continues. The first value is 0, then we get a 1, then we get a 0, then we get a minus 1, then we get a 0. So this is a 0, this is a 0. Every odd term in this Taylor series for sine is going to be 0. So the only Taylor polynomials of interest are the odd degree ones. So let me just scroll through them all again. There's the first degree, there's the third degree, the fifth degree. You see how it's approximating those maximums and minimums better? That's the seventh degree. There's a ninth degree polynomial. That's an 11th degree polynomial. Now we're looking at a 13th degree polynomial and a 15th degree polynomial. You see how good of an approximation it is. You can't really even see it there, but you can see how good an approximation this is now to sine from minus pi, 2 pi to pi for, I think that was an 11th degree polynomial. So as we build these higher degree polynomials, we get better approximations. And this is really building on that idea from Calc 1 where we had a linearization. Look, there's the linearization. It's an approximation to the function really close to the origin. But as we build higher degree polynomials, you can see those approximations get better and better away from the origin. In fact, we can go further away from the origin and get really good approximations now if we take enough terms in the Taylor series approximation. And guess what? That idea of these approximations getting better and better as we add more terms to the Taylor series. So here are the polynomials. The first one was just x, the next one was x minus x cubed, the next one added a term. Notice the difference from one Taylor polynomial to the next is just adding that next term. Everything else stays the same. Here's the fifth Taylor polynomial, the fifth degree one, and here's the seventh. All I've done is add the seventh degree term, and then the ninth, I add a ninth degree term. And so our approximations to the sine function get better and better as we add more terms. Well, I wonder what happens as we just keep doing that. Do we eventually get the entire function? Now we're talking about an infinite series instead of a polynomial. That's exactly where we're going in the next section. But before we do that, let's look at another Taylor polynomial. Well, there's a nice theorem in the book that tells us that this nth degree polynomial centered at A agrees with f up to order n at x equals A. And it's the only polynomial that does this. And what I mean by agrees with f in this case is all the derivatives agree, precisely the condition we had in this box. So this is what we were looking for. We wanted all the derivatives of f and g to agree. And I've now stopped calling it g and I started calling it the nth degree Taylor polynomial. So the nth degree Taylor polynomial and the original function, their derivatives agree up to the nth derivative. That was the goal, and that's what the theorem's telling us. And just a bit of notation, if we actually build a Taylor polynomial centered at the origin, centered at 0, then we call it a Maclaurin polynomial. All right, so the ones we were just building, for example, t sub 3 of x, that polynomial we were building for sine, that's the third Maclaurin polynomial because the center is at 0. Right, it's the third Maclaurin polynomial for sine of x. Let's do one more example. Let's look at now, let's take a more interesting function. Let's take the natural log. The natural log of x, and we're going to build a Taylor polynomial at x equals 1, let's say. So again, to find a Taylor polynomial, what we need to do is calculate all the derivatives. We need to know the value of the function at the center. And we're centering it at 1. And notice I chose 1 because log of 0 isn't defined. Log of 1 is defined. That is 0. But I couldn't calculate this series centered at 0 because the log function is not defined there. But then I need to know all the derivatives, right? F prime. Well, the derivative of log is 1 over x. And the second derivative of log is minus 1 over x squared. And the third derivative of log is, well, now the 2 is going to come down, so I've got 1 times 2, and now it's going to be a positive, and it's going to be over x cubed. Let's keep going. The fourth derivative of log is going to be, the 3 is going to come down with a negative now, so it's 1 times 2 times 3 over x to the 4. And hopefully you can see that, let's call it the kth derivative of this log function at x is going to be, well, there's going to be a negative. We'll work that out in a second. It's an alternating series because it's going positive, negative, positive. For the fourth derivative, I had a 3 factorial on the top, right? It was a negative 3 factorial over x to the 4. So this is going to be, the kth derivative is going to be k minus 1 factorial divided by x to the k. And now I want minus 1 to the power of, well, it's going to involve k somehow. When k is 1, I want a positive, so I'm going to write this as a k minus 1 as well, because when k is 2, I want this to be a negative, and that works. But note also that I can go one step further, because what I really want is this evaluated at a, right? And so I want this evaluated at 1, because that's where I'm evaluating all these derivatives. So doing that gives us minus 1 to the k minus 1 times k minus 1 factorial divided by 1 to the k. So this is very straightforward. This is an alternating sequence, in fact, that has k minus 1 factorial in it. And so let's write out what the nth degree polynomial would be using this formula. Putting this all together, we can just start writing this out. We know what f of 1 is, so I'm just going to write it out in general here. We're going to have f prime of 1 divided by 1 factorial x minus, in this case, 1, plus f double prime of 1 over 2 factorial x minus 1 squared, and so on. And there's n of them, so this goes up to the nth one, evaluated at 1, over n factorial x minus 1 to the n. So we know what f of 1 is. That's 0. We worked it out here. Now, what about the first derivative? The first derivative, that's when k is equal to 1. Plugging that in here, that gives us a positive, I believe. K is 1, this is negative 1 to the 0, and this is k is 1, so this is 0 factorial over 1 factorial x minus 1. The next one is going to be, now k is 2, this is going to be a negative k minus 2, k is 2, so this is 1 factorial divided by 2 factorial divided by x minus 1 squared. The next one will be a positive. It's going to be a 2 factorial over a 3 factorial x minus 1 cubed. The next one's going to be a negative 3 factorial divided by a 4 factorial x minus 1 to the power of 4. And then we're going to keep going with that pattern until we get to the last one. And I don't know whether it's positive or negative, so I'm just going to write it as n minus 1. Depends what n is. And this will be k minus 1 factorial over k factorial, x minus 1 to the power of, n. N is the variable now. So n minus 1 factorial over n factorial. And we can simplify these things, right? This is obviously 0. 0 factorial is 1, so this whole first term is just 1. But then the next term is going to be, well, 1 factorial over 2 is just a half, x minus 1 squared. The next one, 2 factorial over 3 factorial, think about what's happening. This is 1 times 2 over 1 times 2 times 3, so this just leaves the 3, x minus 1 cubed. And then we're going to subtract, well, now we've got 3 factorial over 4 factorial, so this is just going to be a quarter, x minus 1 to the 4, and this is just going to keep going. The next one must be a fifth, x minus 1 to the 5. And then subtract, dot, dot, dot. The last one, again, we don't know whether it's positive or negative, but we do know that it leaves 1 over n as the value, x minus 1 to the power of n. And then there is our nth degree polynomial that is an approximation to the natural log. Let's look at a couple of graphs just to get a feel for what that's doing. This is centered at 1, by the way. So here are our Taylor polynomials. I've just got them printed out. The first one was x minus 1. Let's have a look. So the first Taylor polynomial, remember that the Taylor polynomials build term by term. So the first Taylor polynomial is x minus 1. The second Taylor polynomial is these two combined. The third Taylor polynomial is those 3 terms. The fourth Taylor polynomial is those 4 terms, right? A 4th degree polynomial. And so that's precisely what you can see here. It's a bit mixed up. This is x minus 1. There's the x minus 1. Subtract a half of x minus 1 squared. And there's the x minus 1. Subtract a half x minus 1 squared plus a third of x minus 1 cubed. And so on. So if I graph these things, you can see the first Taylor polynomial there. Right? The Taylor polynomial of degree 1. It's just a straight line. We built this centered at x equals 1, which is why it agrees with the log function exactly at 1. This browny orangey curve is the log function. So they agree there and they have the right slope there because the first degree polynomial is the linearization. But here's the higher degree polynomials, right? There's the third and the fifth. And actually I lie because let's go back. This is the second degree polynomial. That's the second. There's the third. Sorry, second, third, fourth, fifth, sixth. You can tell they're even or odd. There's a seventh, there's an eighth. These are both opening downwards. It's even. This is an odd polynomial. And you can see as that degree of the polynomial gets higher, it becomes a much better approximation to the function in the region between 0 and 2. But it's getting crazy when x is bigger than 2, right? It's getting nothing like. Let's have a look at a high degree polynomial here. This one is really close to the log function most of the way between 0 and 2. But when x is bigger than 2, it's going off and doing crazy things. Well, doesn't that sound like it doesn't converge? Didn't we build an infinite series for log in the previous section that looked a lot like this? And we found that that infinite series, in fact, only converged between 0 and 2. So this connects what we were seeing for infinite series, the idea of an interval of convergence, to these Taylor polynomials. You can see that as you get better and better, bigger and bigger degree Taylor polynomials, they're approximating the function better in some region, but not everywhere. And because that Taylor polynomial is not converging, as I take the limit as n goes to infinity, it's not converging to the function for all x. It's got a center and a radius of convergence. And that's what we'll talk about in the next lecture. Thanks for tuning in.